What if everything you thought you knew about the universe was just the tip of the iceberg? Picture this, floating in the vast emptiness of space, staring at a swirling, shimmering tunnel, a gateway to another galaxy, another time, maybe even another reality. This isn't just science fiction. Wormholes, those mysterious cosmic shortcuts woven into the fabric of space and time, might be more than just a Hollywood fantasy. Think back to that jaw-dropping moment in Interstellar when Cooper plunges into Gargantua, hurtling through a kaleidoscope of dimensions, that cinematic spectacle. It's rooted in real science equations scribbled by Einstein over a century ago, hinting at tunnels that could bend the rules of physics as we know them. But here's where it gets even wilder. Wormholes aren't just bridges across space. They're potential time machines, cosmic glitches, maybe even doors to parallel universes. Imagine stepping through one and emerging in a world where dinosaurs never went extinct, or where you exist in 1,000 different versions. Sounds impossible, right? Yet some of the brightest minds alive today are wrestling with these very ideas, pushing the boundaries of what we think is possible. From quantum entanglement to black hole paradoxes, the theories surrounding wormholes are as thrilling as they are mind-bending. And that's exactly what we're diving into today. 30 of the most incredible, spine-tingling theories about wormholes and space-time travel. We'll explore how these cosmic tunnels could defy gravity, how they might already exist hidden in the folds of the universe, and whether we could ever harness their power. Could they be the key to humanity's future among the stars, or are they cosmic traps waiting to unravel anyone reckless enough to enter? Strap in, because we're about to journey through the rabbit hole of cutting-edge astrophysics, where the line between science and science fiction blurs into something even stranger, the truth waiting to be uncovered. Long before Hollywood turned wormholes into cinematic spectacles, two of the greatest minds in physics laid the groundwork for these cosmic shortcuts. Back in 1935, Albert Einstein and his colleague Nathan Rosen stumbled upon something bizarre while wrestling with the equations of general relativity. Hidden in the math was a strange possibility, tunnels threading through the very fabric of space-time, connecting one distant point to another in an instant. They called them bridges, and on paper they looked flawless. A traveler could theoretically step into one end of this tunnel and emerge light years away, as if space itself had folded to bring distant corners of the universe within reach. But here's the catch: Einstein and Rosen never actually believed these bridges could exist in reality. To them, they were little more than mathematical quirks, elegant solutions to equations that had no bearing on the tangible universe. Imagine an architect drafting a flawless blueprint for a floating castle, only to shrug and say, "Well, that's nice, but gravity exists." That's essentially how these bridges were treated for decades, a fascinating idea with no physical proof. Yet the implications were staggering. If these bridges were real, they wouldn't just warp space, they'd warp time. Step in one side, and you might exit not just in another galaxy, but in another era entirely. Picture a subway system for the cosmos, where black holes acted as the entrances and exits. The only problem: the math suggested these tunnels would collapse faster than a house of cards in a hurricane. To stay open, they'd need something exotic, something with negative energy, a concept so bizarre it sounds ripped straight from a comic book, and that's the irony. What started as a footnote in a dusty academic paper might hold the key to humanity's greatest dream, conquering the vast, empty gulfs between stars. Because if Einstein's bridges can exist, then the universe just handed us a cheat code, one we're still scrambling to understand. For decades after Einstein and Rosen dismissed their own cosmic bridges, wormholes remained trapped in the realm of mathematical fiction until two physicists dared to ask a dangerous question: what if we could actually travel through one? In 1988, Michael Morris and Kip Thorne ripped this idea from the pages of theory and gave it startling new life. They sketched out a blueprint for something once thought impossible: a traversable wormhole, a stable tunnel through space-time that wouldn't snap shut the moment you stepped inside. The secret, a bizarre ingredient called exotic matter. Not the kind you'd find in a lab or a star. This stuff defies everything we know about physics. Picture matter with negative energy, a substance that pushes when gravity pulls, propping open the wormhole's throat like cosmic scaffolding. It's the opposite of normal matter in every way, and here's the kicker: we've never actually seen it. Quantum mechanics whispers that tiny amounts might flicker in and out of existence at the subatomic level, but harvesting enough to stabilize a wormhole. That's like trying to build a skyscraper out of soap bubbles. Yet this wild idea didn't just tantalize physicists, it rewrote sci-fi forever. Morris and Thorne's equations became the scientific backbone of movies like Contact, where Jodie Foster's character plunges through a wormhole network built by an advanced alien civilization. And that's the tantalizing twist. Maybe we're not the ones who'll crack this puzzle. Maybe a species older, wiser, and technologically braver has already done it, threading the galaxy with wormhole highways we've yet to discover. But let's ground this in reality for a moment. Even if exotic matter exists, the energies required to manipulate it are staggering. Think about squeezing the mass energy of Jupiter into a space smaller than an atom. The sheer forces involved would shred anything we could build today, and yet the equations hold. The math doesn't break. That's the maddening beauty of theoretical physics. It dangles the impossible just close enough to make us reach. So while Morris and Thorne's wormholes remain a dream for now, they've given us something just as precious: a roadmap, a signpost in the dark, pointing toward a future where the stars might not be so far away after all. What if the key to time travel has been hiding in plain sight, woven into the very fabric of space itself? Wormholes don't just bend space, they twist time, turning these cosmic tunnels into potential portals to the past or future. Here's how it works. Imagine one end of a wormhole stays parked near Earth while the other gets strapped to a rocket and hurtled to near light speed. Thanks to Einstein's theory of relativity, time slows down for the moving end. While centuries pass on Earth, only days might tick by for the accelerated end. Now step through from the Earth side. You'd exit in the past, like walking through a door into yesterday. But this isn't just a thought experiment. Physicists like Kip Thorne have crunched the numbers, and the math checks out, at least on paper. There's a catch, though. Opening a wormhole to the past doesn't just rewrite history, it risks unraveling it. Take the infamous grandfather paradox. What if you traveled back and accidentally prevented your own birth? The universe despises contradictions, and this one could shred causality itself. Stephen Hawking was so convinced time travel was impossible, he proposed the chronology protection conjecture, a cosmic rulebook preventing paradoxes by snapping any time-traveling wormhole shut before it could be used. Nature, it seems, might have a built-in undo button, yet some theorists aren't ready to surrender. Quantum mechanics offers a wild loophole: parallel timelines. Maybe wormholes don't rewrite history, they branch it, spitting you into a new reality where your actions don't affect your original timeline. Picture a choose-your-own-adventure book where every decision spawns a fresh page. This multiverse twist could dodge paradoxes entirely, turning wormholes into bridges between alternate realities rather than time machines. But before you start drafting letters to your past self, consider the practical nightmare. Stabilizing a wormhole for time travel would require energies beyond anything we can muster. The gravitational forces near a black hole, one proposed anchor point for the wormhole's far end, would rip apart atoms. And even if you survived the journey, there's no guarantee you'd arrive intact. Quantum effects might scramble you into noise before you reach the other side. So are wormhole time machines possible? The universe seems to whisper maybe while laughing at our audacity. For now, they remain a tantalizing what if, a reminder that the cosmos guards its deepest secrets closely. But the very fact that physicists can seriously debate this idea tells us something extraordinary. The line between science and magic might be thinner than we think. Beyond the realm of star-spanning cosmic tunnels lies a far stranger possibility: wormholes so small they flicker in and out of existence in the blink of an eye. Dive into the quantum foam, that seething, chaotic substrate of reality at the Planck scale, where space-time itself churns like a bubbling cauldron. Here, the fabric of the universe isn't smooth and continuous, but a frothing ocean of microscopic fluctuations. And within that foam, some physicists speculate, tiny wormholes could be constantly forming and vanishing, smaller than an atom and lasting barely a fraction of a second. These aren't the stable, traversable tunnels of sci-fi dreams. Quantum wormholes are more like cosmic hiccups, spontaneous, unpredictable, and governed by the bizarre rules of quantum mechanics. Imagine space-time as a sheet of paper crumpled at the smallest scales, with pinprick holes briefly threading through the folds. They might not let you send a spaceship through, but their existence could revolutionize our understanding of reality. Why? Because they might hold the missing link between Einstein's gravity and the quantum world, a theory of quantum gravity, the holy grail of modern physics. Think of it this way: general relativity paints the universe on a grand scale with planets, black holes, and warped space-time. Quantum mechanics, meanwhile, rules the subatomic realm, where particles teleport, entangle, and exist in multiple states at once. The two theories refuse to play nice. They've never been unified, but quantum wormholes could be the bridge. Some models suggest these fleeting tunnels might weave space-time itself out of entangled quantum particles, like invisible threads stitching the cosmos together. The implications are staggering. If space-time is stitched together by quantum entanglement, it would mean the universe is far more interconnected than we ever imagined. A change in one corner of reality could instantly ripple across wormhole threads to another, faster than light, no violation of relativity required. It's a concept straight out of quantum teleportation experiments, but scaled up to cosmic proportions. Yet for all their promise, quantum wormholes remain tantalizingly out of reach. Detecting something that exists for a billionth of a trillionth of a second is, to put it mildly, a challenge. Some researchers hope advanced particle colliders or quantum computers might one day uncover hints of their existence. Others speculate that these wormholes could leave faint imprints in the cosmic microwave background, echoes of the Big Bang's quantum froth. So while we can't yet prove they exist, the mere possibility reshapes how we see the universe. If quantum wormholes are real, they're proof that even the tiniest wrinkles in space-time could hold the keys to the biggest mysteries, from the birth of the cosmos to the fate of reality itself. And that's the wildest part. The answers we seek might be hidden in places too small to see, flickering in and out of existence before we even notice they're there. Black holes have long been the universe's ultimate enigmas, cosmic vacuum cleaners so powerful, not even light can escape their grip. But what if these monstrous voids aren't just dead ends? What if they're secret doorways threaded together by hidden wormholes? This isn't just wild speculation. In recent years, a bombshell theory called ER EPR has electrified the physics world, suggesting black holes might be two faces of the same cosmic coin, connected through space-time tunnels so profound they could rewrite the rules of reality. The idea hinges on a dazzling link between two seemingly unrelated concepts: wormholes and quantum entanglement. Let's break it down. Back in the 1930s, Einstein and Rosen proposed those hypothetical bridges in space-time we now call wormholes. Decades later, Einstein teamed up with Boris Podolsky and Nathan Rosen to describe quantum entanglement, that spooky phenomenon where particles instantaneously influence each other across vast distances, as if they share a hidden hotline. For years, these ideas lived in separate corners of physics, until theorists like Juan Maldaisner and Leonard Susskind dared to ask, what if they're the same thing? That's the radical heart of ER EPR. It suggests entanglement isn't just an invisible connection, it's a physical bridge, a wormhole stitching black holes together across the universe. Picture two black holes born from the same stellar cataclysm, forever bound by an unseen tunnel. Toss an object into one, and it might not be lost. It could emerge from the other, scrambled but intact. This isn't just sci-fi poetry. The math hints it could resolve one of physics' biggest headaches, the black hole information paradox, which asks whether data swallowed by a black hole is truly destroyed, a violation of quantum law. But here's where it gets even weirder. If wormholes really are entanglement made manifest, then the universe might be far more interconnected than we ever imagined. The holographic principle, a cutting-edge idea in theoretical physics, suggests our three-dimensional reality could be a projection of information stored on a two-dimensional surface, like a cosmic DVD encoding everything we see. Wormholes could be the threads weaving that hologram together, with entangled black holes acting as anchors. Of course, there's a catch. These wormholes would be non-traversable, too unstable for even a photon to slip through. They're more like cosmic glue than stargates, yet their existence would mean the universe is fundamentally stitched together by hidden tunnels, a vast, invisible network humming beneath the surface of reality. So are black holes secret wormhole gateways? The equations whisper yes, but nature guards its secrets fiercely. For now, ER equals EPR remains a beacon, guiding us toward a deeper truth that the universe might not just be stranger than we imagine, but stranger than we can imagine. And somewhere out there, in the darkness between the stars, two black holes could be holding hands across the void, bound by a thread of spacetime we're only beginning to unravel. If black holes are the universe's insatiable vacuum cleaners, sucking in everything that crosses their path, then white holes are their mythical opposites, cosmic fire, hydrants blasting matter and energy outward at impossible speeds. Picture a black hole running in reverse, a region of space where nothing can enter, only escape. These bizarre objects aren't just science fiction. They emerge naturally from the same equations that predict wormholes, acting as their hypothetical exits. While a black hole's event horizon is a point of no return, a white hole's horizon would be a point of no entry, violently repelling anything that dared to approach. But here's the puzzle. If white holes are mathematically sound, why have we never spotted one? The answer might lie in their catastrophic instability. Unlike black holes, which form from collapsing stars and persist for eons, white holes would be staggeringly short-lived. The moment they spew out their contents, the sheer energy release could tear them apart in a blinding flash. Some theorists speculate that gamma-ray bursts, those mysterious explosions shooting more energy in seconds than our sun emits in billions of years, could be the death throes of white holes. Imagine a cosmic geyser erupting just once before vanishing forever, leaving behind only an echo of radiation. Even wilder is the idea that a white hole might have already played the ultimate role, birthing our universe. The Big Bang itself shares eerie similarities with a white hole event, a sudden, explosive outpouring of energy and matter from an infinitely dense point. Could our entire cosmos be the other side of a wormhole, the result of some alien universe's black hole collapse? It's a dizzying thought, but the math doesn't rule it out. In this scenario, every black hole in our universe might be sowing the seeds for a new cosmos, with wormholes threading through the multiverse like roots beneath a forest. Yet white holes face fierce skepticism. The laws of thermodynamics favor disorder, and a white hole's orderly expulsion of energy seems to defy entropy's relentless march. Plus, without a mechanism to form naturally, they remain ghosts in the equations, tantalizing, elusive, and just out of reach. But that's the thrill of theoretical physics. Sometimes the most outrageous ideas force us to ask better questions. Whether white holes are cosmic myths or hidden keys to reality, they remind us that the universe still holds mysteries no equation can yet contain. String theory has always danced on the edge of fantasy, a universe where reality isn't made of particles but of tiny, vibrating strings. These threads of energy thrum through not just the 3 dimensions we know, but through 11 dimensions curled up so tightly we've never glimpsed them. And hidden within this labyrinth of extra dimensions, some physicists believe could be the secret to stable wormholes. Take Calabi-Yau manifolds, those bizarre, 6-dimensional shapes where string theory's extra dimensions hide. Picture a garden hose seen from far away. It looks like a simple line, but up close, it's a tube with a circular dimension wrapped around it. Calabi-Yau spaces are like that, but infinitely more complex, folding in on themselves in ways that could, theoretically, pinch space-time into tunnels. These wouldn't be the fragile wormholes of general relativity. Here, the extra dimensions might act like cosmic duct tape, reinforcing the walls against collapse. Then there's the brainworld scenario, one of string theory's wildest ideas. Imagine our universe as a 3-dimensional membrane, or brain, floating in a higher dimensional space like a slice of bread in an infinite loaf. Other brains could hover just millimeters away in these extra dimensions, utterly invisible to us. But gravity, leaking between brains, might weave wormholes between them, cosmic subway tunnels connecting realities stacked like pancakes. The implications are staggering. If brainworld wormholes exist, they could explain dark energy's mysterious pull or even offer shortcuts to parallel universes. Some models suggest these tunnels might naturally form during cosmic collisions, brains smashing together in higher dimensions, leaving wormholes stitched into the aftermath like scars. Yet the challenges are just as dizzying. Stabilizing a wormhole in string theory would require precise control over those curled-up dimensions, something we're nowhere near achieving. And detecting higher dimensional gravity, current instruments might as well be stone tools, but the math holds a tantalizing promise. In the hidden folds of reality, wormholes might not just be possible, they could be inevitable. So while string theory's wormholes remain locked in equations, they remind us that the universe's greatest secrets might be hiding not in distant galaxies, but in dimensions we can't even see. The Big Bang wasn't just a beginning, it was a cosmic pressure cooker, a seething cauldron of energy where the laws of physics as we know them flickered in and out of existence. In those first chaotic moments, space-time itself may have stretched and twisted like taffy, forming microscopic fractures in the fabric of reality, and some theorists believe those fractures could have birthed the universe's first wormholes, tiny, primordial tunnels woven into the infancy of everything. These wouldn't be the carefully constructed wormholes of sci-fi dreams. Think of them instead as cosmic birthmarks, scars left behind when the universe inflated faster than light itself during inflation. The energy densities back then were so extreme that space-time itself might have bubbled like boiling water, with wormholes forming spontaneously in the foam. The wild part, a handful of these tunnels could have survived, lingering in the cosmos like invisible spiderwebs, stretched and warped by 14 billion years of cosmic expansion. But how would we even spot something so ancient and elusive? One clue might lie in gravity's fingerprints. Primordial wormholes, if they exist, would warp the space around them in subtle but detectable ways. Imagine a hidden tunnel threading between 2 points in space. Any object passing nearby would experience a tiny, unexplained tug, as if gravity itself were whispering secrets. Astronomers are already hunting for these anomalies, scrutinizing the orbits of stars and galaxies for gravitational hiccups that can't be explained by visible matter. Then there's the cosmic microwave background, the afterglow of the Big Bang. If wormholes left scars on the early universe, they might have imprinted faint patterns in this ancient light, ripples that today's telescopes are just barely sensitive enough to catch. Some models even suggest these tunnels could act like cosmic lenses, bending light in ways that distort distant galaxies into strange, telltale shapes. The most tantalizing possibility, primordial wormholes might not be lifeless relics. If they've stretched alongside the expanding universe, some could now be large enough to traverse hidden highways left over from creation, waiting for someone bold enough to find the entrance. It's a long shot, but the universe has surprised us before. After all, if space-time could twist itself into knots at the dawn of time, who's to say some of those knots didn't stay tied? Dark matter has always been the universe's quiet ghost, invisible, mysterious, and everywhere. It doesn't glow, reflect, or absorb light, yet its gravitational grip shapes galaxies and bends the cosmos itself. But what if this enigmatic stuff isn't just holding galaxies together? What if it's also propping open cosmic doorways? Some daring theorists suggest dark matter could be the exotic matter we've been searching for, the very ingredient needed to stabilize wormholes and turn them from mathematical curiosities into real, traversable shortcuts through space. Think about it like this: exotic matter, the hypothetical substance needed to keep a wormhole's throat open, has one bizarre property: negative energy. It repels instead of attracts, counteracting gravity's crushing force. Now consider dark matter's strange behavior. We can't see it, but we know it clumps around galaxies like an invisible scaffold, its gravity bending light and sculpting the cosmos. Most theories assume dark matter is just another flavor of ordinary matter. But what if it's something far stranger? Enter the fringe idea that some dark matter particles might carry negative mass. It sounds like science fiction, but the math doesn't rule it out. If even a fraction of dark matter behaved this way, it could naturally gather around wormhole mouths, acting as cosmic scaffolding. Suddenly, two of physics' biggest puzzles, dark matter's nature and wormhole stabilization, could solve each other in one stroke. The same invisible matter holding galaxies together might also be weaving hidden tunnels between them. This theory isn't just elegant, it's testable. If dark matter really is propping open wormholes, their mouths would cluster where dark matter does, near galactic centers, in vast halos around galaxies, or floating in the voids between superclusters. Astronomers might spot their presence through subtle gravitational anomalies, stars orbiting empty patches of space, or light bending around nothing we can see. Of course, skepticism runs deep. Negative mass particles defy our understanding of how matter should behave, and no experiment has ever detected anything like them. But dark matter already defies expectation. We've never directly caught a single particle of it, despite decades of searching. Maybe we've been looking for the wrong thing. The boldest version of this idea: wormholes are dark matter, not just stabilized by it, but made of it. Picture a universe threaded with invisible tunnels, their entrances hidden in plain sight, woven from the same elusive stuff that binds galaxies. If true, the cosmos might be far more connected and far weirder than we ever dared to dream. For now, it remains a tantalizing what if. But that's the beauty of theoretical physics. Sometimes the wildest ideas reveal the deepest truths. And if dark matter really is the universe's secret architect, not just of galaxies but of wormholes too, then the stars might be closer than they appear. Imagine the universe cooling after the Big Bang, space-time hardening like a sheet of ice on a frozen lake. Just as ice fractures under stress, forming intricate patterns of cracks, the infant cosmos might have developed its own fractures, tiny, hidden flaws in the fabric of reality. These wouldn't just be random imperfections. If certain theories hold, these cosmic fault lines could have woven themselves into vast, labyrinthine networks of wormholes, threading through the cosmos like invisible spider silk. The idea hinges on a phenomenon called topological defects. Picture this: as the universe expanded and cooled, the fundamental forces we know today, gravity, electromagnetism, split apart like colors separating in a prism. But this phase transition wasn't perfectly smooth. In some regions, space-time might have crystallized unevenly, leaving behind wrinkles or tears. These defects wouldn't behave like matter or energy. Instead, they'd be more like geometric glitches in the universe's code, places where the rules of physics twist into something stranger. Some of these defects could take the form of cosmic strings, hypothetical one-dimensional cracks in space-time with unimaginable density. A single inch of cosmic string might weigh as much as a mountain, warping space around it like a taut wire pressing into a rubber sheet. Now imagine two such strings crossing or vibrating in just the right way. The forces at play could pinch space-time into a tunnel, a wormhole born not from collapsed stars or exotic matter, but from the universe's own growing pains. Here's where it gets even wilder. These wormholes wouldn't exist in isolation. Like cracks in ice spreading fractally, branching into ever smaller fissures, space-time defects could form interconnected webs. A single fracture in the early universe might have splintered into a self-similar network, with wormholes of all sizes linking distant regions, scales, or even epochs. Need to cross the galaxy, there might not be one cosmic shortcut, but countless, each a thread in a sprawling, ancient tapestry. The implications are dizzying. If space-time defects seeded wormholes, they could lurk everywhere, in the voids between galaxies, nestled within star clusters, or even right here in our solar system. Their fractal nature might mean they operate on all scales, from microscopic quantum bridges to tunnels large enough to swallow stars. Some theorists speculate these networks could explain dark energies accelerating push on the cosmos, with wormhole throats leaking gravitational energy across the universe. But how would we find something so elusive? The answer might lie in gravity's subtleties. A wormhole fault line would warp the space around it, bending light or tugging on stars in ways that betray its presence. Astronomers have already spotted bizarre gravitational anomalies, stars orbiting empty patches of space, galaxies moving as if pulled by unseen hands. Could these be the fingerprints of a hidden wormhole network? There's another tantalizing possibility. If these defects formed in the universe's first seconds, their remnants might have left echoes in the cosmic microwave background, the afterglow of the Big Bang. Strange temperature fluctuations or polarized light patterns could hint at spacetime's hidden fractures, waiting to be decoded. Of course, skepticism is healthy. Topological defects remain theoretical, and no direct evidence confirms their existence. Yet the math behind them is solid, rooted in well-tested phase transition theories. And if even a fraction of these ideas hold, the universe isn't just expanding, it's intricately cracked, threaded with shortcuts woven into its very foundation. So the next time you gaze at the night sky, consider this: the darkness between stars might not be empty. It could be filigreed with cosmic fault lines, ancient, invisible, and holding the keys to the universe's deepest secrets. The holographic principle turns everything we know about reality on its head. What if the three-dimensional universe we experience is just a shadow, a projection from a two-dimensional surface at the edge of space-time? This mind-bending idea, born from black hole physics, suggests that everything we see, galaxies, stars, even our own bodies, might be like a movie playing on the surface of a cosmic bubble, with depth and dimension nothing more than an elaborate illusion. And wormholes, they could be the hidden stitches holding this hologram together, threading quantum information between boundaries in ways we're only beginning to unravel. Picture a black hole's event horizon, the point of no return. According to the holographic principle, every particle swallowed by the black hole leaves an imprint on this surface, like a fingerprint pressed into wet clay. The information isn't lost, it's encoded in a swirling, two-dimensional quantum tapestry. Now imagine two black holes entangled in this way, their event horizons linked by a wormhole. The tunnel between them wouldn't just bridge space, it would act like a quantum fiber optic cable, ferrying encrypted data between the two surfaces. Step into one black hole, and your information might reappear on the other side, scrambled but intact, as if teleported through a hidden backdoor in reality. This isn't just theoretical poetry. In 2013, physicist Juan Maldacena and Leonard Susskind proposed that entanglement, that spooky connection between particles across vast distances, might literally be wormholes in disguise. Their groundbreaking work suggested that when two particles are entangled, a microscopic wormhole links them, invisible to us but woven into the fabric of space-time. The implications are staggering. Every quantum connection we've ever observed could be underpinned by a vast, invisible network of holographic wormholes, stitching the universe together at its most fundamental level. But how does this translate to the cosmos we see? Think of the universe as a giant quantum computer with wormholes acting as the circuitry. Just as electricity flows through wires to power a screen, quantum information might flow through these tunnels to project the illusion of three-dimensional space. The wormholes themselves wouldn't be physical tunnels you could fly through. They'd be more like mathematical relationships, equations that define how information moves between the two-dimensional boundary and the three-dimensional world we perceive. Here's where it gets even stranger. If the holographic principle is correct, then wormholes might not just connect different places in space. They could link entirely different descriptions of reality. A wormhole might bridge a world where gravity operates in three dimensions with a shadow world where it emerges from quantum interactions on a two-dimensional surface. It's like realizing the story you've been reading is actually a translation of an older, denser text, with wormholes serving as the Rosetta Stone between the two. Yet for all its elegance, this idea faces fierce challenges. How do we reconcile the smooth, continuous space-time of general relativity with the discrete, pixelated reality implied by holography? Can wormholes truly encode the complexity of a three-dimensional universe in two dimensions without losing something in translation? These are the questions keeping physicists awake at night. But the holographic principle offers something more profound than answers. It reframes the questions. If wormholes are the glue binding the universe's hidden layers, then understanding them isn't just about unlocking space travel. It's about deciphering the very code of reality, one quantum thread at a time. And somewhere, woven into the fabric of the cosmos, a wormhole might be waiting, not just as a gateway to the stars, but as a key to the universe's deepest secret, that everything we see is just the surface of something far richer and far stranger than we ever imagined. What if every choice you've ever made spawned a new reality, a parallel universe where a different version of you exists? The multiverse isn't just science fiction. It's a serious scientific hypothesis, one that wormholes might help prove. At the heart of this idea lies Hugh Everett's many worlds interpretation of quantum mechanics, which suggests that every quantum decision forks the universe into endless branches. And if these alternate realities exist, could wormholes be the bridges linking them together? Think of the multiverse like a vast cosmic tree, with each branch representing a universe where history unfolded slightly differently. Maybe in one, dinosaurs never went extinct. In another, you took that job offer across the country. These universes aren't just theoretical according to quantum mechanics. They're mathematically inevitable, bubbling into existence every time a particle's wave function collapses. The catch, they're usually forever out of reach, locked away in dimensions we can't access, unless, of course, space-time itself has hidden backdoors. That's where wormholes come in. If entangled black holes can be connected through tunnels, as the ER EPR theory suggests, then why not entangled universes? Some models propose that wormholes could thread through higher dimensions, stitching together separate branches of the multiverse like stitches in a quilt. Picture a tunnel where one end sits in our universe and the other emerges in a reality where the laws of physics are subtly or drastically different. Step through and you might find yourself in a world where gravity is stronger, light moves slower, or the Roman Empire never fell. But here's the twist: traversing a multiverse wormhole wouldn't be like hopping between cities. Quantum decoherence, the process that keeps parallel realities separate, means these tunnels would likely collapse the moment anything tried to pass through. It's like trying to cross a bridge made of soap bubbles. Even if you could stabilize one, the energy required might be astronomical. bending space-time so severely that the journey itself would shred matter into quantum noise. Yet some physicists speculate there might be another way. If wormholes act as quantum observers, they could select a single universe from the multiverse's infinite possibilities, effectively allowing a form of communication between realities without full traversal. Imagine sending a beam of light through a wormhole and having it emerge in a universe where that light's properties are slightly altered, a cosmic Morse code between worlds. The wildest implication: if wormholes can link parallel universes, they might explain some of quantum mechanics' deepest puzzles. Take Schrödinger's cat, simultaneously alive and dead until observed. Could that superposition be a fleeting connection to another reality, a wormhole flickering open just long enough to borrow a cat from a neighboring universe? It sounds absurd, but the math doesn't dismiss it outright. Of course, skepticism abounds. The multiverse remains untested, and wormholes bridging realities are pure speculation. But the allure is undeniable. If even a fraction of these ideas hold, then wormholes aren't just shortcuts through space. They're keys to the grandest cosmic library of all, where every possible version of reality sits waiting on the shelf. And somewhere in the quantum static between the universes we know and those we can't yet imagine, a tunnel might already be open, whispering secrets across the void. What if our universe isn't the first or the last in an endless cycle of cosmic rebirth? Cyclic cosmology paints a breathtaking picture, a universe that expands, contracts, and explodes anew in an eternal loop, with each iteration separated by a Big Bang. But here's the twist: wormholes could be threading these cycles together, stitching each universe to the next like links in an infinite chain. Imagine space-time not as a one-way street, but as a Möbius strip where the end of one cosmic era curves seamlessly into the beginning of another, connected by hidden tunnels lurking in the void. The idea builds on the ekpyrotic model, where our universe is just one membrane floating in a higher dimensional space, occasionally colliding with a neighboring brain to trigger a new Big Bang. These collisions release unimaginable energy, birthing fresh universes, but between the collisions, wormholes could act as cosmic umbilical cords, ferrying quantum information from one cycle to the next. Think of it as a cosmic game of telephone, where the laws of physics themselves whisper through these tunnels, subtly shaping each new universe in the sequence. Some theorists take this even further. If wormholes survive the violent collapse and rebirth of the cosmos, they might carry echoes of past universes into our own. Picture stumbling upon a region of space where the constants of nature shift inexplicably, gravity slightly stronger here, the speed of light fractionally slower there. These anomalies could be scars from a previous cycle, imprinted on our reality through wormholes that refuse to fully close. It's like finding a faded message in a bottle washed ashore, hinting at a world that existed before time as we know it began. But how would such tunnels endure the apocalypse? The answer might lie in quantum foam, that frothing sea of virtual particles at the smallest scales. Even as the universe crunches toward its fiery end, microscopic wormholes in the foam could remain stable, anchored by exotic physics we barely understand. When the next Big Bang erupts, these tunnels might stretch and expand like cosmic taffy, weaving the fabric of the new universe with threads from the old one. The implications are staggering. If wormholes bind sequential universes, they could explain why our cosmos seems so finely tuned for life. The fundamental constants, the strength of gravity, the mass of electrons might not be random. They could be hand-me-downs from countless cycles, refined over eons until the conditions for stars, planets, and life itself emerged. In this view, wormholes aren't just shortcuts through space, they're time capsules, carrying the DNA of reality itself across the ages. Yet challenges loom. Cyclic models require a mechanism to reset entropy, avoiding the heat death that should make each universe more disordered than the last. Wormholes might offer a loophole, siphoning entropy into higher dimensions or balancing it across cycles like a cosmic ledger. But until we find evidence, perhaps in the cosmic microwave background's faintest ripples, these ideas remain exhilarating speculation. So the next time you hear about the Big Bang, consider this: it might not have been the beginning. It could be just one heartbeat in an endless cosmic rhythm, with wormholes humming beneath the surface, keeping time for a universe that's lived and will live countless lives. And somewhere in the darkness between the stars, a tunnel might yawn open, not to another place, but to another epoch altogether. Building a wormhole from scratch isn't just an engineering challenge, it's a defiance of physics as we know it. Picture trying to thread a needle with a rope made of smoke. Yet some of the brightest minds in theoretical physics have sketched blueprints for artificial wormholes, and the steps involved read like a recipe for rewriting reality itself. The first ingredient: exotic matter with negative energy density, a substance that pushes against gravity instead of surrendering to it. Think of it as cosmic anti-gravity glue, propping open the wormhole's throat against the crushing weight of collapsing space-time. Quantum mechanics whispers that such matter might flicker in and out of existence at the smallest scales, but harvesting enough to stabilize a tunnel wide enough for a proton, let alone a person, would require bottling the energy of a dying star. Then comes the geometry. To bend space-time into a traversable tunnel, you'd need to sculpt it with precision beyond anything we can achieve today. One hypothetical design involves two charged black holes spinning in perfect sync, their event horizons stretched into funnels until they nearly touch. Between them, a throat could form a bridge threaded with exotic matter to keep it from snapping shut. The math behind this, inspired by Einstein's equations, is dizzyingly complex, but the takeaway is simple. Stabilizing the tunnel would demand control over gravitational forces so fine-tuned, even a single atom out of place could trigger a catastrophic collapse. But the real showstopper is energy. Recent calculations suggest creating a wormhole just 1 meter wide might require converting the mass of Jupiter into pure energy, more than all the energy humanity has produced in its entire history, compressed into a space smaller than a marble. And that's just to open the door for a fraction of a second. To keep it stable, you'd need a power source orders of magnitude beyond anything we can conceive, harnessing technologies like Planck scale manipulation or quantum vacuum energy extraction, concepts so advanced they border on magic. Here's where it gets even wilder. Some theories suggest we might not need to build wormholes from scratch at all. Instead, we could grow them. Imagine injecting a seed of exotic matter into the quantum foam, then coaxing it to expand using concentrated dark energy, the same mysterious force accelerating the universe's expansion. Like blowing up a balloon, this could inflate a microscopic wormhole into something traversable. The catch: dark energy remains one of cosmology's greatest mysteries. We don't know how to bottle it, let alone direct it with surgical precision. Yet the most audacious ideas come from quantum field manipulation. If we could somehow twist the Higgs field, the invisible ocean that gives particles mass, we might locally alter the rules of gravity, creating a bubble of space-time ripe for wormhole formation. It's like turning a patch of ocean into a temporary whirlpool by stirring the water in just the right way. Theoretically, advanced civilizations could use this to weave wormholes like spiders spinning silk, threading them across the galaxy. Of course, the roadblocks are staggering. We'd need to master technologies that currently exist only in equations, gravity manipulation on par with black holes, energy harvesting beyond Dyson spheres, and materials that laugh in the face of cosmic forces. But the fact that physicists can even plot this path tells us something profound. The universe might not forbid wormholes, it just demands a price we're not yet ready to pay. And somewhere out there, in the far future or in a civilization we've yet to meet, someone might be scribbling the final drafts of a blueprint we've only just begun to trace. Among the most daring ideas in modern physics is the notion that we might pry open wormholes not with black holes or exotic matter, but with subatomic particles. Specifically, high-energy neutrino beams, those ghostly messengers that streak through our planet by the trillions every second, barely interacting with anything. Some theorists speculate that under extreme conditions, these elusive particles could warp space-time so violently they'd tear microscopic wormholes into existence, if only for a fleeting instant. The math behind this idea traces back to the bizarre properties of neutrinos themselves. Unlike electrons or quarks, neutrinos are nearly massless, traveling at speeds so close to light that time barely touches them. When accelerated to energies beyond anything naturally occurring, think a billion times more powerful than the most extreme cosmic rays, their gravitational fields could become significant, subtlety bending the fabric of space-time around them. Now imagine a beam of these ultra-high-energy neutrinos focused to a needle's point, slamming into a target. The collision wouldn't just release energy, it might twist space-time into a knot, creating a wormhole so tiny only quantum particles could slip through. But here's the catch. Even if such an event occurred, the wormhole would likely collapse faster than the blink of an eye, vanishing before we could detect it. That hasn't stopped scientists from probing the possibility. Particle colliders like the Large Hadron Collider, or LHC, already accelerate particles to unimaginable speeds. Could they, in theory, push neutrinos hard enough to trigger a wormhole? The answer teeters on the edge of maybe. The LHC's current neutrino beams aren't nearly energetic enough, but future upgrades or next-generation colliders, like the proposed Future Circular Collider, might inch closer to the necessary thresholds. Skeptics argue that even with infinite energy, the odds are vanishingly slim. The space-time distortions required would demand conditions far beyond what any collider could realistically achieve, perhaps energies comparable to those at the Big Bang itself. Worse, there's no guarantee a microscopic wormhole would behave predictably. It might evaporate instantly or tunnel into higher dimensions, leaving no trace. Yet the tantalizing possibility lingers. If particle colliders could ever crack open even a transient wormhole, the implications would rewrite physics. It could offer the first experimental evidence that wormholes aren't just mathematical curiosities, but real, tangible phenomena lurking in the quantum foam. For now, the idea remains firmly in the realm of speculation, but in a universe full of surprises, that's exactly where the most revolutionary discoveries often start. Quantum entanglement has long been called spooky action at a distance by Einstein, but what if that spookiness is literally rooted in the fabric of space-time? The wild idea that entangled particles might be invisibly tethered by microscopic wormholes, called the ER EPR conjecture, blurs the line between quantum mechanics and general relativity in ways that still baffle physicists today. Picture two electrons born from the same atomic event, instantaneously mirroring each other's spins across light years as if sharing one mind. According to traditional physics, this connection shouldn't be possible. Information can't travel faster than light. Yet if space-time itself is threaded with wormholes too small to see, these particles might not be communicating at all. They could simply be two ends of the same hidden tunnel, touching through a shortcut in reality. This isn't just poetic speculation. In groundbreaking work, physicists like Juan Maldacena and Leonard Susskind showed that the math describing entangled particles EPR perfectly mirrors the equations for wormholes ER. It's as if the universe handed us two different maps of the same terrain, one from quantum theory, the other from gravity. Take the famous quantum teleportation experiments, where scientists transmit information between entangled particles faster than light should allow. If you interpret those results through the lens of ER EPR, the teleportation isn't magic, it's particles whispering through a subatomic wormhole too fleeting to detect. But how do we test something so far beyond our senses? The answer might lie in black holes. When two black holes become entangled, say, by forming from the same collapsing star, their interiors could be connected by a wormhole, even if their event horizons are galaxies apart. Theorists have simulated this using holographic models where quantum bits on a black hole's surface encode information that tunnels through to its partner. In 2023, Google's quantum computer even mimicked this effect, showing entangled qubits behaving as if linked by an Einstein-Rosen bridge. The experiment didn't create a real wormhole, but it proved the math holds, at least in a simplified baby universe. Critics argue this is all elegant analogy, not proof. After all, quantum entanglement works flawlessly without invoking wormholes, and no experiment has ever detected spacetime curvature at the quantum scale. Yet supporters counter that ER equals EPR could solve physics' biggest headache, the black hole information paradox. If information swallowed by a black hole isn't lost but teleported through a wormhole to another point in space-time, it neatly preserves quantum theory's sacred rule: information can never truly vanish. The most tantalizing implication: if every entangled pair in the universe is secretly linked by microscopic wormholes, then space-time at its smallest scales might be a seething network of tunnels. The vacuum of empty space could be a quantum subway system, buzzing with connections we've only just begun to map. It's a vision of the cosmos where the deepest mysteries, from entanglement to dark energy, might all trace back to the same hidden architecture: wormholes stitching reality together one quantum thread at a time. Plasma, the fourth state of matter, is far from just the stuff of stars and lightning. It might also hold the blueprint for nature's own wormholes. Across the cosmos, vast filaments of superheated plasma stretch for thousands of light years, weaving through galaxies like cosmic spiderwebs. These aren't just chaotic rivers of charged particles. Some physicists suspect their twisted, helical structures could accidentally mirror the geometry of wormholes, creating transient tunnels in the fabric of space itself. Picture the sun's corona, a seething maelstrom of plasma loops dancing in magnetic fields. Now scale that up to galactic proportions, where filaments of ionized gas, threaded with currents millions of times stronger than Earth's entire power grid, snake through the void. Under extreme conditions, these plasma structures can warp space-time around them, twisting electromagnetic fields so violently that they mimic the gravitational curvature of a wormhole's throat. It's not a perfect replica, but the resemblance in the math is uncanny. Simulations show that under the right magnetic pressures, plasma filaments could fold space into temporary pseudo-wormholes, short-lived, but real enough to bend the paths of particles passing through. Lab experiments are already chasing this idea. Using devices called plasma focus machines, scientists have generated tiny, self-organizing plasma filaments that exhibit bizarre behavior. When zapped with high-energy pulses, these filaments twist into double helix shapes, creating regions where electromagnetic fields become so knotted. They distort local space-time metrics in ways reminiscent of theoretical wormholes. No, these aren't traversable tunnels yet, but they're proof that nature might already be sculpting wormhole-like structures in the most unexpected places. The key lies in plasma's fluid dynamics. Just as water spiraling down a drain creates a funnel, plasma spinning in ultra-strong magnetic fields could twist space-time into similar vortices. Some models even suggest that pulsars, those rapidly spinning neutron stars sheathed in plasma, might naturally form microscopic wormholes in their magnetospheres, where magnetic field lines snap and reconnect with enough force to pinch space-time itself. Skeptics argue these plasma structures lack the negative energy density needed for true wormholes, but supporters counter that quantum effects in extreme plasmas could generate fleeting bursts of exotic matter, propping open these tunnels for fractions of a second. Whether they're cosmic shortcuts or just fascinating analogs, one thing's clear: if wormholes are possible, nature might have been experimenting with them long before we started drawing equations on chalkboards. The universe, it seems, has a flair for dramatic recycling, turning even the most chaotic plasma storms into potential gateways. What if consciousness itself could weave wormholes into existence? At the intersection of cutting-edge physics and ancient philosophy lies a radical idea that the fabric of reality and the fabric of thought might be inextricably linked. Panpsychism, the view that consciousness is a fundamental property of the universe like gravity or electromagnetism, suggests that even particles might possess rudimentary awareness. Now imagine that collective consciousness under the right conditions could bend space-time itself, creating tunnels not through exotic matter or black holes, but through sheer mental energy. This isn't as far-fetched as it sounds. Quantum mechanics already blurs the line between observer and reality. The act of measurement changes a particle's behavior, as if the universe responds to our attention. Some interpretations suggest consciousness plays an active role in collapsing quantum probabilities into definite states. Extend that idea further, and a sufficiently focused mind, or a network of minds, might influence space-time geometry on macroscopic scales. Think of Tibetan monks who claim to manipulate reality through meditation, or laboratory experiments where group intention appears to subtly alter random number generators. Could these be faint echoes of a deeper principle, that consciousness doesn't just perceive reality but participates in shaping it? Theoretical frameworks like orchestrated objective reduction (ORCH), or proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, take this further. They argue that consciousness arises from quantum vibrations in microtubules, tiny structures within brain cells, which might interact with the fundamental geometry of space-time. In this view, every thought could send ripples through the quantum foam, and under extraordinary circumstances, those ripples might coalesce into wormholes. It's as if the universe has a hidden psychic layer where focused intention warps the rules. Science fiction has toyed with this concept for decades. In Solaris, Stanislaw Lem envisioned a planet-sized consciousness that physically molded space to human thoughts. Real-world analogues might be found in near-death experiences, where individuals report traversing tunnels of light descriptions eerily similar to wormhole traversals. Skeptics dismiss these as neurological glitches, but what if the brain, in extremis, taps into latent space-time architectures we don't yet understand? The challenges are obvious. No known mechanism allows consciousness to generate negative energy or curvature in Einstein's equations. Yet the overlap between quantum biology and relativity hints at uncharted territory. If microtubules really do quantum computations, could they exploit spacetime's inherent looseness at microscopic scales? Some models even speculate that advanced civilizations might harness collective consciousness as an energy source, sculpting wormholes through sheer will. Whether these ideas ever graduate from speculation to science, they force us to confront a profound question. Is the universe a cold machine, or a living network where mind and matter are two sides of the same coin? Wormholes might not just be cosmic shortcuts, they could be the universe's way of thinking itself into new possibilities. Gravitational waves, the ripples in space-time caused by cosmic cataclysms, have already revolutionized astronomy. But what if these ripples hold whispers of something even stranger? Hidden in the faint tremors detected by observatories like LIGO and Virgo could be the fingerprints of wormholes, warping the fabric of reality in ways we're only beginning to decode. When black holes collide, they send shockwaves through space-time like a mallet striking a drum. The resulting gravitational waves follow a predictable pattern, a crescendo of spiraling frequencies followed by a sudden ring-down as the new black hole settles into silence. But if a wormhole lurked nearby, the signal could twist into something far more peculiar. Picture echoes bouncing off the walls of a cave, except in this case, the cave is a tunnel through space-time. Gravitational waves passing through a wormhole's throat might ricochet between its ends, creating faint, repeating pulses in the data. These wormhole echoes wouldn't match the clean, singular ring-down of a black hole. Instead, they'd resemble a cosmic call and response, with each ripple delayed just milliseconds as it traverses the hidden tunnel. the math behind this idea is surprisingly solid. Simulations show that wormholes with certain geometries, especially those lined with exotic matter, would distort passing gravitational waves in telltale ways. The echoes would carry subtle shifts in frequency, like a voice echoing down a long hallway. Some physicists, like Vitor Cardoso of Lisbon's Instituto Superior Técnico, have even reverse-engineered what these signals might look like in LIGO data. The challenge, distinguishing them from noise or other cosmic oddities, like the bizarre vibrations of fuzzy black holes or quantum foam fluctuations. Future detectors could tip the scales. Next-generation observatories like the Einstein telescope or space-based LISA will listen for gravitational waves with unprecedented sensitivity, catching frequencies too faint or low for current instruments. If wormhole echoes are real, these machines might finally hear them. Even more intriguing, certain wormhole models predict that colliding black holes could briefly open a wormhole between them during merger, leaving behind not just echoes, but a gravitational wave signature that flickers like a candle in the wind as the tunnel stabilizes, then collapses. The implications are staggering. If we could confirm a wormhole's signature in gravitational waves, it wouldn't just prove these tunnels exist, it might reveal where they are. Scientists could triangulate their positions, mapping hidden shortcuts through the cosmos. And if wormholes really are entangled black holes, as the ER EPR conjecture suggests, their gravitational wave handshake might encode secrets about quantum gravity itself. Of course, skepticism remains. Alternative explanations for echo-like signals abound, from exotic compact objects to quirks in space-time's quantum structure. But the hunt is on. Teams are already scouring LIGO archival data for anomalies, training AI to spot the subtlest deviations from black hole norms. Every unexpected blip could be a breadcrumb leading to the biggest discovery in physics, a whisper from the other side of a cosmic tunnel waiting to be heard. Dark energy's relentless push on the cosmos, stretching space itself faster and faster, remains one of physics' most baffling mysteries. But what if the answer isn't some unknown force lurking in the void? What if it's been leaking out of wormholes all along? This provocative theory suggests these cosmic tunnels aren't just shortcuts through space, they might be sieves, dripping vacuum energy into our universe and fueling its accelerating expansion. The math behind this idea hinges on a peculiar property of wormholes. Their throats could act like one-way valves for quantum fluctuations. Picture the quantum foam, that seething sea of virtual particles popping in and out of existence at the smallest scales. Normally, these particles annihilate almost instantly, borrowing energy from the vacuum only to repay it moments later. But near a wormhole's throat, the extreme curvature of space-time might disrupt this delicate balance. Negative energy densities required to prop open the tunnel could interfere with the foam's natural ebb and flow, allowing tiny amounts of energy to escape like steam from a kettle. Over billions of years, this slow leak could accumulate into the repulsive force we call dark energy. Critics argue this sounds like a cosmic accounting trick. How could microscopic wormholes add up to something as vast as dark energy's grip on the universe? The answer lies in scaling. If primordial wormholes formed in abundance during the Big Bang, as some inflation models suggest, their combined influence could be staggering. Even if each tunnel contributes only a trickle of energy, a universe threaded with countless such structures might collectively exert the exact anti-gravitational push we observe. Simulations show that under certain conditions, wormhole networks could mimic dark energy's equation of state, a mathematical fingerprint that matches observational data eerily well. The boldest twist, this might solve two puzzles at once. If wormholes are both dark energy source and the universe's hidden scaffolding, they'd reconcile the cosmic acceleration we see with the missing mass problem. Quantum field theory predicts the vacuum should contain vastly more energy than we observe, the infamous cosmological constant problem. But if wormholes are siphoning off that energy, redistributing it through their tunnels, it could explain why the vacuum's density appears fine-tuned for life. Of course, the challenges are immense. No direct evidence links wormholes to dark energy, and competing theories like quintessence or modified gravity still dominate the conversation. Yet the elegance of this idea is undeniable. Instead of inventing new physics to explain cosmic acceleration, we might simply be overlooking the hidden architecture already woven into space-time. And here's the kicker: if wormholes really are fueling the universe's expansion, they're not just relics of the past, they're active players shaping our future. As space stretches, these tunnels might stretch with it, their leakiness increasing over time. One day, far in the future, they could tear space apart at the seams, not with a bang, but with a whisper, a silent unraveling of reality itself. Until then, they remain cosmic enigmas hiding in plain sight, perhaps holding the key to everything we don't yet understand. Imagine matter that moves in perfect, repeating loops not just in space but in time, a structure where atoms dance to an eternal rhythm, cycling endlessly without energy loss. This isn't science fiction, it's a time crystal, an exotic phase of matter first theorized in 2012 and later created in labs using supercooled quantum systems. Now, physicists are asking an even wilder question. Could these bizarre materials hold the key to stabilizing wormholes, turning them from fleeting mathematical quirks into usable cosmic highways? Time crystals break the conventional rules of physics. Unlike ordinary matter, which settles into equilibrium, time crystals perpetually oscillate between states, like a clock ticking forever without being wound. Their secret lies in quantum entanglement, locking particles into a synchronized rhythm that resists entropy's decay. Now picture embedding such a structure in a wormhole's throat, a tunnel where space and time are already stretched to their limits. The time crystal's repeating pattern could act like a cosmic metronome, counteracting the wormhole's tendency to collapse by constantly resetting the geometry of its walls. It's like using a pulsating scaffold to shore up a tunnel in shifting sand, where each pulse reinforces the structure against collapse. The math behind this idea is still in its infancy, but early models are tantalizing. In 2021, researchers exploring quantum gravity suggested that time crystals could generate the negative energy densities required to prop open wormholes, not as a static exotic matter plug, but as a dynamic, self-renewing quantum phenomenon. Think of it as replacing the cosmic duct tape holding a wormhole open with a self-healing material, one that repairs itself with every tick of its internal clock. Lab experiments are already hinting at possibilities. When scientists manipulated time crystals in controlled environments, they observed fleeting phenomena resembling microscopic spacetime loops, regions where time's arrow seemed to bend back on itself. These aren't wormholes, of course, but they suggest that matter structured in time, not just space, might interact with relativity in ways we're only beginning to grasp. If scaled up, could a sufficiently large time crystal bend spacetime into a stable loop, creating a traversable wormhole? The leap from lab curiosities to cosmic shortcuts is enormous, but the theoretical bridge exists. Critics argue that time crystals alone can't overcome the titanic energies needed for macroscopic wormholes, yet hybrid approaches are emerging. Combine time crystals with exotic matter, and suddenly the recipe looks less impossible. Imagine a wormhole throat lined with a lattice of time crystals, their rhythmic oscillations tuned to amplify negative energy effects. The result might be a tunnel that doesn't just endure, but actively resists collapse, like a heartbeat keeping space-time alive. The implications would rewrite physics. A time crystal-stabilized wormhole wouldn't just connect distant points in space, it could lock time loops into its structure, allowing for controlled journeys across eras. Need to visit ancient Rome, tune the crystal's rhythm to cycle in sync with that epoch's space-time curvature, and step through. It's the closest thing to a time machine we've ever theorized that doesn't instantly vaporize itself. Of course, the hurdles are cosmic. Time crystals today exist at near absolute zero, barely larger than a few atoms. Scaling them to wormhole proportions would demand technologies we can't yet fathom. But the universe has a way of turning yesterday's impossibilities into tomorrow's breakthroughs. And if nature already toys with time crystals in quantum labs, who's to say the cosmos hasn't forged its own versions in the hearts of neutron stars or the depths of black hole accretion disks? The marriage of wormholes and time crystals might sound like a fever dream, but in the tangled web of quantum gravity, it's just another thread waiting to be pulled. And somewhere in the darkness, a crystal could already be ticking, marking time for a gateway we've yet to find. Neutron stars are nature's ultimate pressure cookers, stellar corpses so dense, a single teaspoon of their material would weigh 1 billion tons on Earth. Their cores crush matter into states so extreme, protons and electrons fuse into a swirling sea of neutrons, and the very laws of physics twist under the strain. But what if these cosmic anomalies aren't just dead stars? What if their incomprehensible density warps space-time so violently, it rips open hidden doorways deep inside them? Some theorists now speculate that the cores of neutron stars could be cradling something far stranger than neutron soup, microscopic wormholes threaded through their hearts like veins in a cosmic body. The idea stems from the sheer extremity of conditions inside these stars. Under pressures 100 trillion times greater than Earth's atmosphere, space-time itself could contort into shapes we've never seen. General relativity allows for scenarios where the star's core folds inward, forming a tunnel so tightly wound, it's more like a knot in space than the sci-fi wormholes we imagine. Unlike black holes, which devour everything that crosses their event horizons, these neutron star wormholes would be self-contained, trapped in a delicate balance between the star's crushing gravity and the quantum forces fighting to keep matter from collapsing entirely. But how would we ever spot something buried so deep? The answer might lie in pulsars, those rapidly spinning neutron stars that beam radiation like cosmic lighthouses. Pulsars are precision timekeepers. Their pulses arrive with such regularity, deviations of even a nanosecond stand out. And here's where things get interesting. Some pulsars exhibit bizarre timing glitches, sudden jumps in their rotation, rates that defy conventional explanations. Could these hiccups be the gravitational echoes of a wormhole flexing inside the star? A handful of astrophysicists think it's plausible. As the wormhole's throat wobbles under tidal forces or quantum fluctuations, it could subtly alter the star's moment of inertia, causing the pulsar's spin to stutter. Other anomalies, like unexplained X-ray flares or bursts of gravitational waves from otherwise quiet neutron stars, might also betray a hidden tunnel's presence. Imagine a wormhole burping up exotic particles or gravitational ripples as space-time adjusts around it, like a submerged submarine releasing bubbles as it dives. The boldest version of this theory suggests that some neutron stars might not even be stars at all, but holographic shells disguising wormhole mouths. Their apparent solidity could be an illusion with a real action happening inside the tunnel. If true, these objects wouldn't just be stellar curiosities. They'd be nature's own intergalactic subway stations waiting for us to decode their timetables. Of course, skepticism abounds. Neutron stars are already so extreme, adding wormholes might seem like overkill. Alternative explanations for pulsar anomalies like starquakes or superfluid vortices in the core are far more mainstream. But the math doesn't rule it out, and in theoretical physics, that's often enough to keep an idea alive. After all, if neutron stars can turn matter into spaghetti and spin faster than a kitchen blender, why couldn't they bend space-time into a knot? If future telescopes catch a pulsar doing something truly inexplicable, maybe a rhythmic pattern of glitches or gravitational waves with odd harmonics, it might be the universe nudging us toward a revelation. Hidden in the heart of these dead stars, a doorway could be waiting not to another place, but to a deeper understanding of how space, time, and matter intertwine under pressure too extreme for even light to escape. Stephen Hawking's most unsettling revelation wasn't about how black holes devour matter. It was about how they might erase the universe's very information. In the 1970s, he showed that black holes slowly evaporate, emitting faint radiation that carries no trace of what fell in. If true, this would violate quantum mechanics' sacred law. Information can never be truly destroyed. For decades, physicists wrestled with this paradox, arguing whether black holes are cosmic shredders or if information somehow escapes. But buried in the math lies a radical solution: wormholes might be nature's ultimate backup drives, encoding swallowed data in their twisted geometry. At the heart of this idea is Hawking radiation itself. As virtual particles pop into existence near a black hole's event horizon, one falls in while the other escapes, stealing a tiny bit of the hole's mass over eons. The problem: those escaping particles appear random, bearing no relation to the stars, planets, or atoms that form the black hole. It's like burning a library and claiming the smoke particles contain every book's text, seemingly impossible. But wormholes offer a loophole. If black holes are secretly connected to other regions of space-time via Einstein-Rosen bridges, information could tunnel through, imprinting itself on the radiation in ways we can't yet decode. Imagine a sealed letter dropped into a black hole. The wormhole might fax a copy to another universe, preserving the original message while the ink fades in ours. The stakes got even higher when physicists proposed the firewall paradox in 2012. If information must escape a black hole, quantum mechanics demands an inferno of high-energy particles at the event horizon, a firewall that would vaporize anything crossing it. But general relativity insists falling into a black hole should be uneventful, with no fiery barrier. Wormholes could resolve this standoff by acting as cosmic diplomats, negotiating between the two theories. Data wouldn't need to burn its way out. It could take a hidden exit through a wormhole's throat, emerging elsewhere unscathed. This way, no firewall is needed, and both quantum mechanics and Einstein's equations emerge intact. Recent breakthroughs in holography lend startling weight to this idea. The AD-S/CFT correspondence, a framework linking gravity to quantum field theory, suggests black holes encode all swallowed information on their surfaces like a hologram. Wormholes in this model are the threads stitching that hologram together, ensuring data isn't lost, just translated. Picture a black hole as a scrambled hard drive. The wormhole is the recovery cable linking it to an external backup we can't see. Even as the drive degrades, the data persists elsewhere, woven into the fabric of space-time itself. Critics argue this solution feels too convenient, a mathematical sleight of hand that doesn't explain how information traverses the wormhole. But experiments with quantum teleportation offer intriguing parallels. When particles are entangled, information can jump between them instantly, as if traversing a microscopic wormhole. Scale that up, and black holes might exploit a similar quantum highway, their interiors entangled with distant regions through space-time tunnels too fleeting to detect. The implications are profound. If wormholes preserve information, then reality might be far more resilient than we thought, with no true deletion, only transformation. So next time you hear about Hawking radiation or black hole evaporation, remember the universe might not be losing information at all. It could just be filing it away in the ultimate cosmic archive, a labyrinth of wormholes humming quietly in the dark. Imagine a galaxy threaded with invisible highways where civilizations hop between stars not with rockets, but through wormholes, cosmic subway tunnels humming with transit. This isn't just speculative fiction. If traversable wormholes exist, they could transform interstellar travel from a pipe dream into a routine commute, stitching distant worlds into a connected web. Picture a network older than human history, built by a species that cracked the code of space-time long before we crawled from Earth's oceans. Their abandoned stations might still linger in the asteroid belts or gas giants of nearby star systems, dormant relics waiting to be reactivated. The Fermi paradox, the eerie silence of the cosmos despite its vast potential for life, takes on new dimensions with this theory. If advanced civilizations have already woven wormhole networks, they might not need to colonize galaxies the slow way with generational ships or warp drives. Instead, they'd expand through hidden doors, leaving little trace for telescopes to spot. No sprawling Dyson swarms, no fleets of von Neumann probes, just whispers of traffic through tunnels we can't yet detect. This could explain why we don't see obvious signs of galactic engineering. The real infrastructure is tucked into the fabric of space itself, invisible to conventional astronomy. But there's a darker twist. Wormhole networks might not unite civilizations, they could isolate them. Imagine a galactic internet where only certain species have the password. Older, more advanced cultures might gatekeep these shortcuts, monitoring entry points to screen for threats or quarantine dangerous upstarts like humanity. It's a chilling solution to the Fermi paradox. We're not alone, but we're stuck in the cosmic suburbs, barred from the interstellar freeway until we prove ourselves worthy or harmless. Archaeology of the future could look nothing like we expect. Instead of digging for ruins on Mars, we might scan black holes or neutron stars for unnatural anomalies, geometric patterns in accretion disks, gravitational wave signatures that ripple too precisely. The wreckage of a wormhole station, if found, wouldn't resemble metal and circuits. It might be a sculpted spacetime defect, a knot of folded dimensions disguised as a pulsar's blink. And if we ever stumble upon one, the real question won't be how to activate it, but whether something's still listening on the other end. Humanity's first encounter with alien intelligence might not be a radio signal or a spacecraft. It could be stumbling into a backdoor left ajar in the solar system, brushing against a technology so advanced it looks like nature until you see the seams. The galaxy may already be bustling with civilizations passing like ghosts through walls we didn't know were doors, and if we ever learn to knock, someone might finally answer. One of the most chilling theories in modern physics isn't about black holes or dark matter. It's about empty space. The quantum vacuum, that seemingly calm void between stars, might not be as stable as we think. Lurking within it could be a hidden trapdoor, a lower energy state that, if triggered, would rewrite the laws of physics in a cascading wave of annihilation. This nightmare scenario, called vacuum decay, sounds like apocalyptic fiction until you realize that poking holes in space-time might be the very thing that kicks the universe over the edge. At the heart of this doomsday scenario lies the concept of the false vacuum. Think of the universe's current state like a marble resting in a shallow dent on a hillside. It's stable for now, but there's a deeper valley below, a lower energy state that would fundamentally alter how forces like electromagnetism and gravity operate. Normally, the marble stays put, but give it enough of a jolt, say, from a high-energy particle collision, or in this case, a wormhole's creation, and it could tumble down, unleashing a bubble of true vacuum that expands at the speed of light, erasing everything in its path. Here's where artificial wormholes enter the danger zone. Stabilizing one requires manipulating space-time with energies rivaling those of the early universe. The equations suggest that concentrating such extreme curvature in one place might act like a cosmic pinprick, weakening the false vacuum's delicate balance. Picture a soap film stretched taut, poke it with a needle, and the tension snaps, tearing the entire surface apart. Similarly, a lab-made wormhole could be the needle that pops the universe's quantum bubble. The scariest part, we might not even see it coming. The moment the decay begins, the laws of physics inside the bubble would change so drastically that atoms, light, even causality itself would unravel in ways we can't predict. From our perspective, destruction would arrive without warning, an invisible wall of annihilation rewriting reality as it moves, Could this really happen? The odds are vanishingly small, but physics doesn't rule it out. Nobel laureate Frank Wilczek once compared our universe to a glass resting on a table. It seems solid, but bump it just right and it shatters. Wormhole engineering, if attempted without absolute certainty, might be that fatal nudge, yet some theories offer a sliver of hope. If vacuum decay is possible, nature has likely already stress-tested it. Cosmic rays with far higher energies than our colliders regularly bombard the universe, and so far, space hasn't collapsed. That suggests the false vacuum is more resilient than we fear. Still, when tampering with the fabric of reality, the stakes couldn't be higher. For now, vacuum decay remains a ghost story whispered in physics departments, but one that forces us to ask, are some doors better left unopened? While string theory paints the cosmos with tiny vibrating strings, loop quantum gravity takes a radically different approach, imagining space itself as a sprawling web of interconnected loops. These loops, woven into what physicists call spin networks, form the very fabric of reality at the smallest scales. But here's the twist: where these loops intersect, they might not space time into something astonishing: natural wormholes, threaded through the universe like invisible stitches in a cosmic quilt. Loop quantum gravity rejects the idea of smooth, continuous space. Instead, it suggests space is granular, a tapestry of finite loops carrying quantized areas and volumes. Picture a mesh screen magnified until you see the individual threads. Now imagine those threads are threads of space-time itself, vibrating with gravitational energy. When these loops twist and tangle in just the right way, calculations show they could pinch off segments of the network, creating tunnels between distant points. Unlike string theory's higher-dimensional wormholes, these wouldn't rely on unseen dimensions. They'd emerge from the loop's geometry, like a knot suddenly forming in a tangle of wires. The contrast with string theory couldn't be sharper. String theory's wormholes hide in extra dimensions, curled up in Calabi-Yau shapes or stretched between branes. Loop quantum gravity's tunnels, however, are homegrown, sprouting from the same quantum fabric as everything else. There's no need for exotic matter or negative energy. The loop's intrinsic spin and tension could theoretically stabilize the tunnels from within. It's as if space-time comes pre-equipped with its own scaffolding, capable of bending into shortcuts without cosmic glue. But how would these loop wormholes behave? Simulations suggest they'd be fleeting, popping in and out of existence as the spin network fluctuates. Traversing one might be like stepping onto a moving walkway that appears and vanishes beneath your feet, a quantum gamble where timing is everything. Some models even propose that these tunnels could link different moments in time, not just locations in space, effectively turning the spin network into a clockwork of causality loops. Critics argue that loop quantum gravity remains untested, its predictions hovering beyond current experimental reach. Yet its wormholes offer something string theories don't: a direct link to quantum mechanics without invoking unseen dimensions. If space really is a spin network, then wormholes might not be rare anomalies. They could be as common as knots in a fraying rope hidden in plain sight. The implications ripple outward. If loop quantum gravity is correct, then every cubic inch of empty space might seethe with microscopic wormholes, flitting in and out of existence too quickly to catch. Advanced civilizations could someday learn to freeze these tunnels, expanding them into stable highways. Or perhaps nature already has somewhere in the cosmos. A neutron star's crushing weight or a black hole's spin might be stretching these quantum loops into something traversable. For now, it's a breathtaking what if. But whether wormholes emerge from strings or loops, one truth remains: the universe's deepest secrets might be written in geometry, waiting for us to decode the pattern. What if the universe isn't the ultimate reality, but an elaborate simulation, a cosmic video game running on hardware we can't fathom? It's a mind-bending idea that's gained traction in recent years thanks to philosophers like Nick Bostrom, who laid out a chilling trilemma. Either civilizations go extinct before reaching simulation tech, they choose not to simulate reality, or we're almost certainly living inside someone else's simulation. But here's where it gets even stranger. Wormholes might be the glitches in the matrix, hidden backdoors left in the code waiting to be found. Think of it like this. Every complex system has bugs, unexpected shortcuts, or errors that bypass normal rules. In a simulated universe, wormholes could be the equivalent of debug portals, tunnels that skip entire chunks of rendered space-time to save processing power. After all, why simulate every star in a galaxy when you can just stitch distant points together with a wormhole and call it a day? The universe's apparent speed limit, light's sluggish pace, might not be a fundamental law, but a server-side restriction to keep simulated beings from noticing the shortcuts. This idea dovetails eerily with quantum mechanics' spookiest behaviors. Particles entangled across light years seem to communicate instantly, as if the simulation is cheating by linking them behind the scenes. Wormholes could be the hidden wiring enabling this trick, the universe's way of cutting corners while maintaining the illusion of locality. Even black holes' information paradox, where data vanishes into a singularity, makes twisted sense if black holes are just garbage collectors, compressing unused assets to free up memory. The event horizon, a firewall preventing us from seeing the recycle bin. Bostrom's trilemma looms over all this. If advanced civilizations do run ancestor simulations, statistical odds suggest we're in one. In that case, wormholes might not be natural phenomena, but developer tools leftover admin access points from when the simulation was being coded. Imagine stumbling upon a tunnel that leads not to another galaxy, but to the universe's source code, where the rules of physics are just variables waiting to be tweaked. It's the ultimate conspiracy theory. Reality itself has a backstage, and wormholes are the VIP passes. Of course, the simulation hypothesis has fierce detractors. Physicists like Sabine Hossenfelder argue it's unfalsifiable, a fancy way of saying it can't be tested. Wormholes, if they exist, might just be rare cosmic anomalies with no deeper meaning. But the simulation angle offers one unnerving prediction. If our universe is programmed, its creators might have left breadcrumbs. Wormholes could be those clues, intentionally placed to see if we're clever enough to find them. Like a game designer hiding Easter eggs, they might be waiting to see if we ever knock on the fourth wall, and what happens when we do, the most unsettling possibility. If wormholes are simulation glitches, attempting to traverse one could crash the system. Picture a character in a video game realizing they're just pixels and trying to escape the screen. The program might freeze or worse, reboot. Whether that means vanishing into a null void or waking up in a higher layer of reality is anyone's guess. But one thing's certain, if wormholes ever prove the universe is a simulation, it'll be the ultimate plot twist, not just in science but in existence itself. What if a wormhole isn't just a tunnel through space-time, but something far stranger, a cosmic projector, capable of printing matter and energy across the universe like a hologram flickering into existence? This radical idea suggests that traversing a wormhole might not involve physically moving at all. Instead, the information that makes up your body could be beamed through the tunnel, reassembling you on the other side atom by atom, like a fax machine transmitting a document through space and time. The concept builds on one of quantum mechanics' most mind-bending principles, quantum teleportation. In labs today, scientists already teleport particles, not by physically moving them, but by entangling two particles, then using that link to instantly reconstruct a third particle's quantum state elsewhere. It's like scanning a sculpture, emailing the blueprint, and 3D printing a perfect replica on the other side of the world while the original crumbles to dust. Now scale that up to a human being. A wormhole could act as the ultimate quantum fax, scanning every atom in your body, transmitting their precise quantum states through its throat and reassembling you, or a perfect copy, light years away in the blink of an eye. Critics argue this isn't true teleportation, it's annihilation and reconstruction. The original you might cease to exist at the entrance, only for a duplicate to emerge at the exit, complete with all your memories and consciousness. Philosophers call this the continuity of identity problem. Is the reconstructed version still you, or just a convincing imitation? If every atom is perfectly replicated, down to the quantum spin of each electron, could anyone, even you, tell the difference? Yet the holographic wormhole theory goes even deeper. Some models suggest that matter isn't sent through the tunnel at all, it's projected, like light through a cosmic film reel. Imagine the wormhole's entrance as a lens, warping the quantum information of an object into a compressed signal. The throat of the wormhole acts as a waveguide, preserving that signal as it travels, while the exit lens decodes it back into matter. In this view, the universe is less a collection of solid objects and more a dynamic hologram, with wormholes serving as the projectors that rearrange its pixels on demand. The implications are staggering. If wormholes can holographically project matter, they might explain bizarre astrophysical phenomena like quantum entanglement on macroscopic scales. Take two black holes connected by a wormhole, an idea central to the ER EPR conjecture. Matter falling into one could reappear entangled with matter ejected from the other, not because it traveled through space, but because the wormhole printed it using shared quantum data. This could even solve the black hole information paradox, with the wormhole acting as a cosmic backup drive, ensuring no data is ever truly lost, just translated. But the real shocker, this might already be happening naturally. Some theorists speculate that gamma ray bursts, those incomprehensibly violent explosions in distant galaxies, could be the universe's way of misfiring its holographic projector. If a wormhole's exit lens destabilizes, the projected matter might rematerialize as pure energy, erupting across space in a catastrophic blast. It's a haunting thought. The universe's most energetic events could be glitches in a system we're only beginning to decode. For now, holographic wormholes remain firmly in the realm of theory. The energy and precision required to teleport even a single atom this way are beyond our grasp, let alone a human being. Yet the math insists it's possible, not magic, just physics we haven't mastered. And if the universe truly is a hologram, wormholes might be the pens writing its code, stitching reality together one projection at a time. So the next time you hear about teleportation, remember, the science fiction version stepping through a portal and emerging whole might not be the whole story. The truth could be far stranger and far more beautiful. You might not travel through a wormhole, you might be reborn from it. What if the universe could think not through biological brains, but through structures conjured from pure chaos? Enter the Boltzmann brain, a mind-bending thought experiment suggesting that, given enough time, random quantum fluctuations could assemble a self-aware consciousness out of the void. These hypothetical entities, named after physicist Ludwig Boltzmann, aren't flesh and blood. They're freak accidents of entropy, temporary ripples in the cosmic noise that briefly believe they're real. Now thread wormholes into this puzzle and the stakes get even stranger. Could these cosmic tunnels make Boltzmann brains not just possible but inevitable? The math is as unsettling as it is simple. In an infinite or near-infinite universe, even the most improbable events must happen eventually. Given enough time, particles jostling in the vacuum could, purely by chance, arrange themselves into a functioning brain complete with false memories of a past that never existed. The odds are astronomically low, like flipping a coin and getting heads every single time for 1 billion years straight. Yet in an eternal cosmos, those odds inevitably tip toward certainty. This is where wormholes twist the equation. If space-time is threaded with tunnels linking distant regions, they might act as cosmic accelerators for quantum fluctuations, concentrating entropy in ways that make Boltzmann brains far more likely. Picture a wormhole's throat where space-time curvature reaches extremes. Quantum fields here don't behave like they do in flat space. They warp and ripple under intense gravitational stress. Under these conditions, virtual particles, those fleeting ghosts of matter and antimatter that pop in and out of existence, might linger just long enough to organize into something coherent. A wormhole could serve as a quantum pressure cooker, squeezing randomness into self-awareness. It's the ultimate cosmic irony. Tunnels built to traverse the universe might also be factories for phantom minds. But here's the existential kicker. If Boltzmann brains are possible, how do we know we're not one of them? After all, a brain spawned from chaos would believe itself just as real as you do now, complete with fabricated memories of reading this script. Wormholes heighten this terrifying uncertainty. If they increase the probability of Boltzmann brains, the odds shift that we're the statistical flukes, not the other way around. Some physicists argue this very reasoning disproves the idea, because if Boltzmann brains were common, we'd almost certainly be one, which feels absurd. Yet the wormhole variable complicates things. Maybe we're not typical observers, but outliers in a cosmos teeming with temporary minds flickering in and out of existence, each convinced they're the real thing. The debate splits physicists into warring camps. On one side, skeptics insist Boltzmann brains are mathematical curiosities with no bearing on reality. The energy required to stabilize even a single self-aware fluctuation is so vast, and its lifespan so brief, that nature would favor simpler, more stable structures, like actual brains in actual organisms. Wormholes, they argue, don't change this calculus. Their exotic environments are too violent to nurture coherence. But proponents counter that if the universe is truly infinite, impossible becomes inevitable. And if wormholes amplify those odds by bending quantum probabilities in their throats, then somewhere, somehow, a Boltzmann brain is waking up right now, drowning in the illusion of being alive. There's a haunting symmetry here. Wormholes, often imagined as gateways to other worlds, might also be portals to the most unsettling existential void, a universe where reality itself is a statistical anomaly, and every thought you've ever had could be nothing more than a random spark in the dark. The cosmos may not just be stranger than we imagine, but stranger than we can imagine. A place where even the shortcuts through space-time whisper riddles about what's real and what's just a fleeting glitch in the quantum code. What if wormholes aren't just cosmic shortcuts, but something far more profound, the building blocks of reality itself, woven into the universe like genetic code in a living organism? Picture space-time not as a static stage, but as a dynamic, evolving entity that grows and adapts, with wormholes acting as its DNA, tiny, twisted strands that carry instructions for how the cosmos structures itself. This radical idea, echoing physicist Lee Smolens's theory of cosmological natural selection, suggests that wormholes might not merely connect points in space. They could be the universe's way of remembering how to build itself, one generation at a time. Smolens's revolutionary proposal turns the cosmos into something alive in the most unexpected sense. Just as biological evolution favors traits that enhance survival, universes could reproduce through black holes, each collapse birthing a new cosmos with slightly tweaked physical constants. Wormholes, in this view, might serve as cosmic umbilical cords, threading information about successful universal traits from one generation to the next. Imagine a black hole in our universe spawning a baby universe in its depths, with wormholes preserving the mathematical genes that made stars, planets, and life possible. Those tunnels wouldn't just bridge space, they'd bridge time, carrying the recipe for a habitable cosmos forward like a baton in a relay race. The elegance of this idea lies in its audacity. Wormholes as spacetime genes would explain why the universe seems so finely tuned for complexity. If each iteration of reality inherits traits from its ancestors through these hidden tunnels, then the laws of physics aren't arbitrary, they're learned, refined over eons of cosmic trial and error. A wormhole might encode the ideal strength of gravity or the precise mass of an electron, ensuring each new universe improves upon the last. It's Darwinism scaled up to galactic proportions, with wormholes as the mechanism of inheritance. And here's the haunting beauty of it all. If this theory holds, wormholes could be more than just tools for travel. They might be living artifacts, relics of a cosmic ancestry stretching back to the first universe. The tunnels we dream of traversing could be the fingerprints of a grander process, one where space-time itself evolves, learns, and remembers. Every black hole might cradle a new cosmos in its heart, every wormhole a whisper from a parent universe saying, "Here's what worked for us." So the next time you gaze at the night sky, consider this. The darkness between stars might not be empty. It could be threaded with the universe's own genetic code, written not in molecules but in the curvature of space itself. And somewhere out there, a wormhole might be quietly humming, carrying the blueprint for everything we know and everything we've yet to discover. From black holes birthing baby universes to consciousness bending space-time itself, wormholes have taken us on a journey far wilder than any sci-fi epic. We've glimpsed tunnels threading through quantum foam, linked entangled particles across galaxies, and even pondered whether our reality might be a cosmic simulation with wormholes as its hidden backdoors. Each theory peels back another layer of the impossible, revealing a universe where the line between science and speculation blurs into something extraordinary. Think about the sheer audacity of these ideas: wormholes as time machines, as cosmic fax machines teleporting our quantum blueprints, or as fractal cracks in space-time left over from the Big Bang's fiery dawn. Some theories paint them as nature's subway system, woven by ancient civilizations we've yet to meet. Others suggest they're the universe's own neural network, stitching together reality like synapses in a cosmic brain. Whether they're bridges to alternate dimensions or ticking time crystals keeping space-time alive, one thing's clear: wormholes don't just connect points in space, they shatter our notions of what's possible. And that's the real magic here. Every time we think we've pinned down the rules, wormholes laugh and rewrite them. They're reminders that the cosmos is stranger, messier, and more inventive than we'll ever be. Maybe they're out there, hidden in plain sight, lurking in pulsar glitches, woven into dark matter's invisible web, or flickering in lab-made plasma vortices. Or maybe they're just mathematical ghosts, teasing us with possibilities we're not yet advanced enough to grasp. So what's your favorite wormhole theory? The one that keeps you up at night, staring at the ceiling and wondering if the universe is whispering secrets just beyond our reach? Drop it in the comments. I'd love to geek out with you over these cosmic riddles. And if you're hungry for more mind-bending journeys, hit that subscribe button. The universe is full of mysteries and we're just getting started. Until next time, keep looking up and wondering what's on the other side of that shimmering tunnel in